Okay, good. It's my pleasure to introduce my longtime colleague, Dimitar Sasselov, for today's Origins of Life seminar. Dimitar is originally from Bulgaria, and he studied physics there, got a PhD in physics from Sofia University. And that was back in the days of the Iron Curtain, so he had been admitted to the University of Toronto, so that got delayed enough that when he finally got to go to Toronto, he ended up getting a PhD in astronomy there. And his career, so he was there for a while, and then came to the Center for Astrophysics and Astronomy Department at Harvard. His interests have varied widely over time, beginning with cosmology, going to exoplanets. He's been heavily involved in a lot of the Space Telescope missions to identify a wide range of exoplanets. And then in more recent years, through interactions from the Simons Foundation collaboration on the origin of life that two of us actually helped to start, Dimitar has gotten interested in aspects of the chemistry and has actually transitioned to doing wet lab experiments of spectroscopy. And one of the most amazing things for me is that one of Dimitar's graduate students actually for several years was doing work in my lab. I never thought I'd have an astronomy graduate student working in my lab. It was great. With further ado, please.
Thank you, Jack, and thank you all for having me here. I assume I can lose the mask now. Yes, indeed, that graduate student, all the credit goes to her because she's amazing. Now she's in Seattle as a Sagan Fellow. I think it's the first astronomy Sagan fellowship given to a person who did mostly chemistry for there. But just before I start, people start with disclaimer. My disclaimer is the following. I've done quite a few silly and stupid things in my life, but one of the things up there is giving a talk to a chemistry department which has chemistry in its title. And so I hope that you're soft and accepting of me. So there we go. I'm very excited about this because I think it is going to be very exciting to get the project to fruition, and I feel we are very close to doing that. And I'm going to give you the perspective from my astrophysics background. So that perspective is that starts with photons, as always in astronomy, and then goes to electrons, and the rest is chemistry. So I try to stay more with the photons and the electrons in this. But I'm particularly interested to know where this is happening. And those environments look like Mono Lake, which is a closed basin alkaline lake out in between Utah and California, the California side. So what is really going on that started this, and why are we so excited about this project? Of course, the most important thing is that there is a new prebiotic chemistry paradigm. We talk about research in origins of life. That's the same as saying prebiotic chemistry. Prebiotic meaning chemistry that is going to hopefully lead to the building blocks and emergence of life. And you've heard from the person who developed it here. Well, one of them is, of course, Jack, but the other one is John Sutherland, and I can't move my slide because it tells me that the meeting is being recorded. Okay, now it will work. John Sutherland and Matt Palmer, about 12 years ago, developed the first step.
Sorry, the audience at home is having trouble seeing the screen. You have controls for
the camera?
Yeah.
Yes, maybe.
You want to point it up a little bit?
Can you show me what we see? And then, will be easy to
I want to get
control.
more of the top of your screen.
Uh-huh.
There we go.
No, the bottom is important. The electrons are there. Sorry. There we go. Excellent. Okay. So I call it the heliocentric model for the origin of life, because in the center is the sun. The little h nu there is the ultraviolet photons. Some needed feedstock molecules, and then you get the amino acids, the nucleotides, and the lipids. That's what John Sadowant and Matt Towner managed to accomplish over the last 12 years. We got involved towards the end in that part. Jack was already working on his part even before that, but I certainly only got involved in the last couple of years with my lab and contributing from the astrophysics and geochemistry side of things. What is important to me is that central to this whole thing is the UV light, the UV photons, because the first step, the jump starting of this process is when UV photons produced electrons in the water from some reagent that is ready to let go of them. In this particular case, you see a cycle which involves ferrocyanide. What you see there, of course, is not photoionization, as an astronomer I thought originally. It's photooxidation, meaning that the ferrocyanide just changes state, and which also means that it can relatively easily be returned back to ferrocyanide from ferricyanide with a little help from sulfur dioxide dissolved in the water, which under the range of pH between 6 and 8 is sulfide. The sulfide there helps you cycle in a kind of catalytic way. So you can think of this as a fake catalytic cycle in which UV photons produce those electrons. Those electrons move into the water, in which everything happens, of course. They fairly quickly thermalize and become what we call aquated or hydrated or solvated electrons. And now, being surrounded by polar water molecules, they can both be seen because they have very strong absorption around 700 nanometers. But more importantly, they become a very, very important reducing agent. And that is what is the spark that lights the fire of the prebiotic chemistry. Ferrocyanide, we have confirmed in the last couple of years, is the best and most abundant reagent to do this, but it can be done by other copper cyanide, it can be done by the sulfide itself. In fact, you can just do it with sulfide. But we think there was ferrocyanide there, and certainly by far, that's the most important one. This process is also very wavelength dependent, generally, but particularly ferrocyanide, it's less so. When we talk to an astronomer about wavelength dependence in the UV, they think of a window which spans from X-rays to optical. Here, when I mean wavelength dependence, I mean really cutting it between 220 to 300 nanometers. So what happens then? Two things. If hydrogen cyanide is present in the water, and you can already tell because there is already ferrocyanide in the water, there will be hydrogen cyanide, then that gets reduced by those electrons very nicely. It actually is a process, reductive homologation, which simply means that the hydrogen cyanide grows into something bigger with the help of water. It actually becomes simple sugars, and those simple sugars are shown here. Now, for the astronomers in the room, just don't panic. Don't look at this as chemical formula, and don't try to look at them really. Just think of it as a schematic. as a flow from left to right. Something happens in the left side and flows onto the end there with the red arrow. That's glyceraldehyde. That's the 3-carbon sugar or the 3-carbon glyceraldehyde, the first chiral molecule as well in this whole big network, which starts that way. And you can see already, it takes 7 steps, 6 photons and 6 solvated electrons to accomplish the synthesis of one glyceraldehyde. And that glyceraldehyde will then go on to make nucleotides, amino acids, and even lipid precursors. So 2 important things here. So this is a very robust sequence. So to say, even I can do it. So to me, that is the lowest bar for prebiotic chemistry. If Dimitar can do it, any planet in the galaxy can accomplish this. So we believe that this chemistry was happening on the early Earth, probably on early Mars, in many planets. Doesn't mean that it will end up emerging life, but this part is quite robust. Quite robust, but also very important, as you will see, to be robust all the time for a long time, because what comes next is less robust, it's more fickle. This part has to be always there. And that's about it. Now, I want to now concentrate with you on the spark that lights the fire, because that's the UV light, and that's what I know and understand best. And to me, to simplify things, there are 3 major roles that UV light plays in this. And in a sense, this slide will act as my outline for my talk, 1, 2, and 3. So the first one is obvious. Anybody in physics, my colleagues always ask me, so what's the source of energy? There is the source of energy. It's the UV photons which produce the solvated electrons. That's what's driving. There is, of course, the energy which is pre-existing in the very strong CN bond in the cyanide. But, from a physics point of view, there is your source. At least you need that. You cannot just have the CN bond there do something, because it won't. The second thing, which is very important, to me, maybe this is the most important thing I've learned from my experience with this, is that you need selection. Chemistry is very messy, promiscuous, you choose your word. It produces a lot of stuff. Even in the most clean chemical synthesis, you always have byproducts, intermediates, waste products, you name it. On top of it, it's racemic and has multiple isomers with different stereochemistry. Same atoms like to be in different sorts. Biochemistry doesn't like that. Biochemistry doesn't even work with that. So selection is very important. High yields of the products you want is very important. That means that the yields of everything else have to be low. You have to eliminate them. UV light is great at doing that. Temperature can be the source of energy, the temperature gradient, chemical gradient. There are a lot of sources of energy in the universe, but UV light, meaning light or photons in the right energy range between 4 and 6 electron volts, are just right to both help you synthesize and photodestruct. Photosynthesize and photodestruct. Without the destruction, the synthesis is no good. You end up with a mess. You do end up with a mess. With the selection, you end up with life. And I don't think there is any other agent but photons that can accomplish those 2 things simultaneously and so well. So the third one is very interesting, and I even don't know how much important it is. I feel it is very important. Some of us feel it's very important, but it's so little explored or understood that the jury is still out. It's called self-repair. It is something which people in biochemistry have already worked a little bit on. It's obviously has something to do with medicine and treatments. You see, if you damage DNA or RNA using UV light, you would like to repair it. Of course, there is an enzyme for that. There is an enzyme for everything. But interestingly, that enzyme uses light to enact the repair. So then some smart chemists realized that why do you need the intermediary go-between of the enzyme? Can that same light repair what was already damaged? That's what self-repair is. I'll show you an example of that. Okay, so 3 roles for UV light. Wavelength dependence and flux are important. So let's talk about those. What is the environment in which we are going to use the UV light? We don't know, but the best guess we have, and so far the chemistry works under conditions which correspond to this. A closed basin lake, which can concentrate the reagents you need. Most importantly, the cyanides. So the atmosphere on an early Earth or similar rocky planet is most likely oxidizing because it's determined by the redox state of the mantle. So the major part reservoir for anything in chemistry or energy on a rocky planet like the Earth for a very long time, multiple billions of years, is the mantle, the silicate mantle. That silicate mantle in the beginning is reducing. The metals, the iron, which is the most common one, is fully mixed, but soon it differentiates. During that process of differentiation, there is a major redox change in the mantle. It depends on the mass of the planet and some other subtleties, but generally speaking, you have a transition in which the mantle is less reduced, which then controls the surface and the atmosphere, and you end up with an atmosphere which is also less reduced. On top of that, atmospheres, as those of you who study exoplanets, are very prone to being photochemically eroded by their stars, by the sun. What happens essentially, you start losing hydrogen. Hydrogen is the major loss in an exoplanet or planet atmosphere which is sufficiently close to its star to be in a habitable zone where we can talk about liquid water. So the result of that is that even if you start or push on the planet a reducing atmosphere, it will very quickly get rid of it. The current estimate is 10 to the 5 years, which is super fast compared to the lifetime of a planet. So what happens is you end up with an atmosphere with carbon dioxide and nitrogen, with some water, of course. Most of the water is not in the atmosphere. And then those other things, hydrogen cyanide, carbon monoxide, NOxes, and sulfur dioxide, they're minor species. So how are we going to do the cyanosulfidic chemistry, which needs cyanide in huge quantities, and it needs sulfur in less huge quantities, but it needs sulfur, when both of those species are minor components of the atmosphere? Where are you going to get them from? Well, you have to be patient and accumulate them in sediments. So that is why we have that picture. And that brings me back to the UV light now. Okay, so if that is this stage where we are going to have the prebiotic chemistry happen, then what is going to determine the UV light? Wavelength dependence or flux dependence? Well, that was a question which was kind of worked on. A lot of people have thought about UV light in aqueous reservoirs on the early Earth and Mars. But we needed to know really precisely, because I was buying very expensive custom-built lab equipment for that purpose. So being a theorist, I guess Jack didn't mention that to you, but most of my career I've been a theorist. I thought, well, theory will lead the way. Let's estimate how we do that. And my graduate student then who did that, Sukriti Ranjan, and I went on to actually determine exactly what to tell the company which is going to manufacture, custom build our laser pump probe system. And that's what we got. This part here, below 200 nanometers, is always blocked. This part there, the light blue, under above 300 nanometers is never, well, always available. I shouldn't say never blocked. But basically what happens today is the yellow part, which is called UVC light, is blocked by the activity of the biosphere. oxygen gas in the atmosphere and ozone and an ozone layer high up in the atmosphere. They block this yellow part, which is UVC light. There was no life before life originated, so it's easy. You have UVC light. And that UVC light is roughly between 205 and 300 nanometers. And then on it's UVB and UVA, but UV light as we call it. So this is kind of a good estimate for what the solar spectrum very roughly looked like 4 billion years ago. And these are two examples of just the atmosphere and 1 meter depth of water, the lake, in other words, what they attenuate. And the main reason you have this cutoff here is carbon dioxide. Even a small amount of carbon dioxide in the atmosphere will do that for you. Very nice. Now, why is this actually important? Was in one of my first slides. I had a kind of a label there which says, no hydroxyl radicals are produced. That's actually very, very important for biochemistry. Hydroxyl radicals are produced when you have UV light below 200 nanometers. Just a little bit below 200 nanometers, you start photolyzing water and you produce those radicals and they would kill the organic chemistry badly. So in other words, this whole chemistry that I'm talking about doesn't work if you allow UV light below about 200 nanometers. On the other hand, it works nicely just above it. So it's just perfect. Not surprisingly, we're here, but that's the anthropic principle. So UVC light reaches the surface, that's great. And we have to say that from astronomy point of view, you have to worry about the total flux, that's the star mostly, because the attenuation in the atmosphere is kind of, you either have it or you don't have it, as you see. So I don't care about the little loss of flux that actually is there. What I care is cutoffs, and that's really good. So the total flux is just the star. The wavelength dependence depends on many things. The atmosphere and the lake, we're still working on it, but generally we now know what the agents are that produce this. Both of them are important for different reasons. The total flux is obvious. The fewer photons you have, the fewer electrons will produce. Your jump starting will be with a battery. If you actually ask somebody, your neighbor, to help you jump start your car, and their car needs to be jump started, obviously both of you are in trouble. So that happens with M dwarfs. M dwarfs, as we see them and observe them today, in that part, you see I already cut off here the carbon dioxide. So this is at the surface radiance, are actually producing less UV light in that part of the UV spectrum. They may be producing more in X-rays, but less in that part of the spectrum, which matters to us. And that's actually an example of an Earth-like analog. Well, there is no Earth-like analog around this star. AD Leo is the denomination of a star which is particular M dwarf that was observed to have a great flare in 1985. It was very, by chance, caught and observed with multiple wavelengths, and we still use it as an example. These stars have great flares all the time, so they're not that rare. It's just difficult to catch one. Anyway, so you can see to orders of magnitude difference. And so one of the things which we are trying to do regarding flux is trying to see how the chemistry works with flares, as opposed to just constant flux. And Paul Rimmer and John Sutherland are doing this in Cambridge. So that is to be determined in the future. In the meantime, let's go back to the early Earth and the sun. The sun didn't have that problem. It had enough flux for this chemistry to work. By the way, I want to say that my job in this team collaboration with Jack and with John and the others, I feel my job, I don't know, Jack agrees, but is to keep everybody, I wouldn't say to keep everybody honest because I don't have a clue about the chemistry they're doing, but to keep everybody at the right fluxes and as much as possible the right astrophysical and geochemical conditions. So that means particularly the right fluxes. So we, even though initially, and to this day, John and sometimes Jack use a little bit too much flux just to speed up things, we always do our experiments at the right range of fluxes and they still work. So that's a great, good news. Okay, so there is a nice story here, actually, now that I think of it. And the story goes as this. So we are working with Sucrit before I have a lab, so I'm doing theory, to determine this cutoff and to order my equipment, which is supposed to reproduce this spectrum, by the way. That's actually the custom part of it. And we're looking for all kinds of molecules, agents like hazes and stuff, which would cut off different parts of it so that we can then order the right thing, which is expensive. And so eventually we do, and of course we publish the paper later on about that, but we have this long list, laundry list of molecules, one blocks this, another blocks here. And, you know, we kind of couldn't find much to worry about. What you see is kind of the final product here, except there was this big question about sulfur dioxide and hydrogen sulfide. At that time, the chemistry was purely cyanosulfidic. John was just using HS-, which is the dissolved version of a hydrogen sulfide gas in water. And so basically, Sucrit goes to Cambridge and gives a talk, like graduate students do, you know, visiting the partners, and gives a talk in the morning, sometime 11. And by the afternoon, I get this email. We tried a new experiment and it worked great. So apparently, you know, Sucrit was telling them how we're concerned about sulfur dioxide, a special case which blocks some, but not. But then, of course, John is sitting there, as he tells me, and thinking, sulfur dioxide, there's a lot of it, more than hydrogen sulfide. Well, that's sulfide, bisulfite or sulfide in the water when it's dissolved. We haven't tried any of that chemistry with it. And suddenly there is this big opening. You can actually use sulfide in some of this chemistry. And in fact, you should, because if you do the calculation, which, as you see, we even did a paper on that a year later, was that you will get millimolar levels of sulfide, but you'll get only less than micromolars levels of hydrogen sulfide or HS-, because the solubility is different and Henry is low, you know, in water. And there is other factors, so it ends up being orders of magnitude less. And the result is actually that the sulfide works better for some things. It's not for everything. So the current picture is we have to use the sulfur species for that. And in the last 3 years, that actually has essentially blossomed into a situation in which we have a whole new branch to that chemistry, thanks to John Sadowant and Ziwei Lu, but we got a little bit involved in that, which we call the carboxysulphate chemistry, which is a branch of that, simply takes the dissolved carbon dioxide and the bicarbonate you will have in alkaline lakes, together with the sulfide. Sulfide produces your electrons with the UV radiation, and it actually can fix carbon dioxide and produces very valuable products. So the current picture is that this is now an inherent part of that chemistry. It does a lot of things. One of them, for example, is I particularly like it protects and concentrates the aldehydes, the glyceraldehyde and glycoaldehyde, by having the adducts, which are with sulfur. The carboxysulphate chemistry, it does some sulfur when you modify or thionate some of those molecules that you know and love because they're in our bodies, like nucleotides, nucleobases. Sulfur makes them more photoreactive. So you actually open up channels which you didn't have before. And some of them are really like magic. It kind of changes one stereoisomer in the other just with one photon, because there is a sulfur. And the best part about the sulfur is you can get rid of it very easily afterwards, and you have your canonical nucleotide. Very, very fun thing. Anyway, that's the story I want to tell you, but it actually pays to work together as a team because we interact with each other. And I think heuristically, including the astrophysics and the geochemistry, the geophysics into this prebiotic chemistry helps everybody. It is indeed a team effort. And I think to some extent it makes sense. Well, somehow life did emerge on this planet, and if you follow what this planet was like and the environments there, you're more likely to hit the right chemistry, as opposed to if you try to imagine it completely on your own. Okay, the selection part. Now, the selection part is very fun for me, and that's how I got really into the lab and everything, because it was almost obvious to me as a naive astronomer that what we have in life today, and some of those are conserved, so they were in life early on, like the basic molecules, particularly of RNA and DNA, have to be UV stable if UV was the factor that synthesized them and brought them together into the RNA and DNA. I mean, that's a no-brainer, isn't it? So then you can reverse that and say, oh, if I prove that, if I find evidence for that, then I can reverse and say, well, that's an evidence that UV light was an important agent. So kind of the reverse of that. And it turns out to be the case. But I'm past this now, where I'm more worried about these high yields that I told you about. Origin of life, the prebiotic chemistry, in other words, is not a one-step process. That's, I guess, everybody in any community would agree with that. It's a multi-step synthesis. And in multi-step synthesis, chemists have a thing, a daemon, which they call the arithmetic daemon problem. When you have a multi-step synthesis, you have to pay attention to your yields at every step, because the final yield of your product goes as the average yields or the yields of every step to the power of n, which is the number of steps. So you have 10 steps, you produce yields of a half, which normally would be considered great, but how much are you going to get for your final product at the end? 0.5 to the power of 10? Good luck. At some point, it becomes astronomically small numbers. In other words, it doesn't work. So selection is not only being clean in the lab and not contaminating and producing a mess. Selection is critical for all this to work, because you're not getting anywhere in your multi-step synthesis if you do not care about purification. And you cannot send a graduate student to the early Earth to do that for you. It has to be done in a natural, organic way, UV light, in other words. Not only UV light, but also maybe stopping along the way and stockpiling. Crystals do that very well. So you do 8 steps, and then at step number 8, you have actually a particular organic molecule. I'm not going to show it now, but you can ask me afterwards, which actually crystallizes. That's a great way to beat the arithmetic daemon, because then the crystal can stay there and purified. And then you start from the crystal and do another 7 steps, and then you have pyrimidine nucleotides. So that's one way. Of course, the no-brainer part is high yields at every step, but you can't always do that. And what UV light does for you, the selection part, it eliminates the undesirable byproducts, the isomers, the wrong steroids isomers. It hopefully also helps you with the problem of maximization. In other words, the chiral puzzle of life. Why is life chiral? Well, because function of the polymers will require that. But during the prebiotic chemistry, you have to beat the arithmetic daemon. If once you are beyond glyceraldehyde, all your intermediate products are 50-50 because of racemization, and you haven't dealt with that, there goes your arithmetic daemon and high yields, right there. So stockpiling is important, and the whole picture is probably something like this. You have to sediment, use sedimentation to take the very small amounts of hydrogen cyanide in the atmosphere and concentrate them on the bottom of a lake. Closed basin lakes works the best this way. Then you may go through evaporation, just these are geological timescales, hundreds and even thousands of years. That's what you need to accumulate enough ferrocyanide. You will probably, during those thousands of years, have some metamorphic processes happening, intrusions. For those who are geologists here, there is an intrusion, lava floods, meteorites hitting, These are thermal agents, which actually produce more cyanide salts for you. And then finally use what you've accumulated there. So that's the stockpiling part. So you shouldn't worry about not having enough hydrogen cyanide in the atmosphere. You will never, that will never work if you rely on the tiny amount of hydrogen cyanide and sulfur dioxide in the atmosphere or the other agents for that matter. You have to stockpile them. And then, at some point, you will have everything to do that chemistry. Unfortunately, this process has never been seen in the geological record on the Earth. The first and most important factor is nobody has bothered to look. So fortunately now there are a few people who are starting to look. But maybe the more important factor is that as far back as we see, with any rocks that are 4 billion years old, 3.7 or so, and are not completely metamorphized, show signatures of life. In fact, a lot of life, stromatolites, you name it. And so basically, you're not going to see this if life is already there. So the point which we made with John and John there in this review is go to Mars and try to find the chemistry on Mars. Or try to find the fossils of life. Just find the chemistry. Whatever proxies are left there for ferrocyanide and cyanide salts, or the salts themselves, probably not, but so we have great hopes that one of these days, maybe Jezero is the place, will actually at least confirm those few initial steps, particularly the carboxysulphate chemistry, the one which involves the carbon dioxide and the sulfide, produces some really long-living things like oxalate and acetate, and you may be able to see examples in the samples from Mars. And that will be great. It will tell us at least that, at least in the starting the fire and growing the fire part of this prebiotic chemistry and the origin of life, we are on the right track. So that actually is a good story, but I haven't told you how we actually know what we know. The chemists, of course, have told you that. John was here, Jack has told you how they do their part of the work. But understanding those mechanisms and being able to pinpoint the wavelength dependence and flood dependence, which are important for the environmental factors, really begs, the question is, do you understand the mechanism and do you know the rates? And to a great extent, I see this, as the main reason for my lab to exist. So I like to ask the why question. Okay, it has these three roles, but why? Why does UVC light play those roles? I mean, in other words, between 4 and 6 electron volts for those molecules in particular. Well, the first one is easy. You have enough energy to not ionize. I told you it's photooxidized, but could be ionization to produce those potent reducing agents, the sulfate electrons. The other ones are not so obvious, but all of them share the same kind of general physical characteristics. They're short-lived, short timescale processes. The first one takes tens of femtoseconds, the photooxidation and the sulfate electrons are produced. Then the sulfated electron lasts typically in neat water for about 300 nanoseconds. So that's a very long period of time, by the way. So you have enough time to diffuse and to do chemistry. So nanoseconds is chemistry at large. Femtosecond and picosecond is the chemical reaction happening. And that's what you have in 2 and 3. That is the balance between selectivity, in other words, destroying the some isomers and keeping others. Why are some of those nucleotides so UV stable? Well, just a little twist and change in the isomer and it's destroyed. That is because there are internal conversions that are extremely fast. Basically, let's take adenine here, the base, the A from AGCT. Okay, so it's in this ground state here, and then UV excites it to the first excited state here somewhere. And then, it lives there for a while, but it has this ability to pucker. And in some of those molecules, very few of those molecules, the Born-Oppenheimer approximation is broken. The nuclei and the electronic clouds are supposed to be decoupled. You can solve the equation separately. But occasionally they are coupled. Spin-orbit coupling, very strong spin-orbit coupling will do that for you, but occasionally they have coupled. And then you have this very interesting intersection, avoided crossing, some people call them in dynamics, but in this case, they call conical intersection, which suddenly bring you down to the ground state. You have to get rid of the energy somehow, and that's the VC here, the vibrational cooling, but you're surrounded by water molecules. Water is perfect for taking that energy out. So those, like adenine, are extremely photostable because they have non-radiative pathways to get rid of the energy. If you change something in the adenine, just a little bit, an isomer, which by the way will work in your DNA and you wouldn't know it, but if you change that, it becomes extremely UV unstable. It actually gets stuck in those higher levels and sits there for nanoseconds, which for a molecule is a lifetime, and something grabs it while it's excited. Either the water destroys it or it gets grabbed into some other chemical reaction. The guys that are in our flesh and blood today all have this property of having backdoors, non-radiative ways to get rid of the energy. And then you add sulfur, and you start playing with intersystem crossings, triplet states, flipping of the electron spin, and you get very interesting intermediate chemistry, because now you go to the triplet and sit there for nanoseconds. And then finally, if you have polymers, you start having charge transfer opportunities in that polymer. And this is the fun part, which I told you about, the self-repair. So how do you study all this? In order to study all this, you need a pump probe system, a laser pump probe system, which can do spectroscopy for you, because all of these energy states, of course, as the astronomers in the room would know, have very well-defined spectral lines, but you have to do it fast. You have to do it at the time scales at which it happens, femtoseconds, picoseconds, nanoseconds. And systems like that exist. So what you see here is mostly off the shelf, with the exception of those two boxes, the set of crystals that convert the red light of the femtosecond pulse laser system here into UV light. And this is the part which Sukrit Ranjan and I were working on theoretically, because we had to order those from Lithuania, by the way, and those crystals and the whole boxes, they're the best, and be able to reproduce the UV spectrum of any star we wanted, the early sun, the late sun, M dwarf, whatever you want. So of all this system, that's actually the fun part and different from other pump probe systems. But otherwise, it works just like any pump probe. You pump with UV light your sample right there, and you probe it with the red light, which is then dispersed into a spectrum. So you see the absorption or emission lines there. Now this has a mid-infrared spectrometer, so we do UV visible all the way to the mid-infrared. And I will just give you one example. I talk a lot about the solvated electrons. And I told you when an electron is in the water and it gets hydrated after about 50 picoseconds, it gets well hydrated, all the water molecules around it, and it just sits there, you know, negative charge, but big negative charge. It has a very strong red absorption line, and we can see it. This is the theory and experiment about the line in units of energy here, in units of wavelength here, so whichever you like. It's shown as an emission line. For some reason, chemists like to show absorption lines and emission, but you can get used to that. That's an absorption line. That's delta absorbance here. And, you know, theory is based on this kind of modeling. These are water molecules, and this is the solvated electron, big kind of lonely single electron waited to do something, reduce some hydrogen cyanide. It's the hydrated electron. This spectrum is from our system, Corina Kufner, who is a great postdoctoral lab manager. She does this, and you can see the spectrum is this wavelength. This is time. So these are multiple spectra here, thousands of spectra stacked on top of each other. And this is not the spectral line. It is actually how the spectral line decays. So you pump here once at 0.5 seconds. That's the UV pump. You produce the electrons, and then it decays over a microsecond. And you can actually take cut here or cut it there, and then you can plot it as a decay. Okay. And if you want to know what the concentration is and what the rates are, you look at the very tip, which looks very sharp on this scale because the scale of 1 microsecond. But if you go to picoseconds right there, it will look like this. There it is. That's the peak. So we can see all this. And not only we can see it, we can measure it. And that's how we actually know both the mechanisms of many of those reactions and know the rates. And then we can do all kinds of tweaks depending on what kind of plant you have, what kind of lake you may have, and so on. So this has a lot to do with how you produce and use the sulfated electrons. It also has a lot to do with the selectivity. You know, how the canonical monomers that we still have in our bodies are UV stable while the isomers are not. So you beat the arithmetic demon in that way, but you also produce, you know, particular functional oligomers or polymers, which will then do the function for you. And there you have a different problem. Once your monomers are into a polymer, that whole story of the individual monomers being photostable is no longer saving you from destruction. If you have a polymer, and especially a polymer that you want to be functional, to always do the same thing as opposed to kind of become a big mess, they also have to be photostable in a way. But now with the polymer, it is not an issue of being photostable. With the polymer, it's an issue of being functional. And that generally means that if something goes wrong, you can quickly repair it. So that's where the self-repair comes in. You know, and there is a very nice paper by Jack's group, Kim et al. From this year, where they show you purely chemically how you can, and you probably do, start with all kinds of different nucleotides, the monomers for RNA and DNA. And then you have a bunch of oligos which are different. And over multiple rounds of templating, copying, you eventually choose one or the other in large proportions. This, on top of that, has to survive the UV light. So all this is happening under the same UV light. Why? Because you have to make the monomers. The monomers are not made by the cells, which have just started, the protocells. They take the monomers through their lipid bilayers, you know, membranes from the outside. So you need the UV light. But then that same UV light is going to do some damage, lesions is the word biologists use, to your polymers, those little strands with the monomers. So this is where self-repair comes in. Or let's be more general. This is where you have to understand what are the mechanisms in which this same UV light that produces your oligomers also affects basically the well-being and the functioning of those oligomers. And then you have a set of timescales again. You know, in physics, we really like to talk about timescales. So the damage or the first effect is always very fast, less than 5 picoseconds. But then if you do have charge recombination, that is the longer. And whether it takes 20 to 300 picoseconds or nanoseconds is life and death. I told you nanoseconds is just too long. You know, if things happen in nanoseconds, then it's too long. And we're just now starting to understand how this works. And by the way, this is true not just for prebiotic chemistry. This is true for biochemistry as far as I can see. There is not that much work that has been done on this topic. It's very kind of new to everybody. And my postdoc, Corina Kufner, is really one of the experts on that. So let me show you one example of how this works or doesn't work. So you have a little oligo of RNA or DNA. In this case, it will be DNA with just 4 bases. Just 4 bases. There it is here: G, guanine; A, adenine; and TT. So from AGCT again. So the UV light comes in, and if there are 2 T's next to each other, quite often a lesion occurs. That is a chemical defect where the 2 T bases actually merge or bond together. This oligo now becomes dysfunctional. If it happens in your skin, you get skin cancer. You know, that's kind of what dysfunctional means. Now, what Corina found out, well, others in her group, but then she took it one step further, found out is that if a second UVC photon, and again, it's UVC, by the way, it's in the same range of 4 to 6 electron volts. If a second UVC photon comes in, usually the G or the A takes it in, but now they do a charge transfer. They don't produce a lesion, they do a charge transfer, which always end up at the TT lesion and opens it up in a fashion which is very similar to how modern enzymes in your body do it. That's why we don't get cancer, skin cancer every time we go to the beach, but it doesn't work for any set of bases. So in other words, the words matter here, or what Corina found is that in some cases it works great, in some cases it doesn't work. And so there is here now a new set of selection pressure, you would say, or selectivity that UV and self-repair impose on this. And I have to say we don't understand it. I'll leave it there and say it's very fun to study it, but I have the hunch that it's probably going to be important once we get those protocells, well, once Jack gets those non-enzymatic self-replicating RNAs in protocells, because it will determine where those protocells are going to evolve into. They will have to live with this UV light for quite a bit, and that will determine as an important environmental pressure in which direction they're going to evolve. So does UV sculpt the molecular inventory? Question mark. I don't know, but it seems like it does. And, you know, in summary, it's a really fun ride. It's an extremely interesting kind of opportunity to merge what we get from astrophysics and geochemistry with something which is, I would have thought, is the domain of the Department of Genetics, where Jack was residing, and I had to take the subway to get to it, so far away. So it's very, very fun, and I really thank you very much, and of course my team for being part of this. Thank you.
Thank you very much. We have time for questions. So, yeah, Andre.
It's a question about the hydrated electron. So you said that wavelengths less than 200 nanometers would create a situation where this chemistry wouldn't work. So I'm assuming that is somehow due to the fact that the water now is directly absorbing the UV when I said, and then you create hydroxyl radical. So at longer wavelengths, then I assume that electron has to come from some other source, not from water itself. And so I guess that's my question: is creating electrons, what's happening, you know, to the radicals that you're creating, you know, the origin of these electrons? I'm guessing these must be dissolved salts of some kind of chloride.
Yeah, so that's a very good question. So in the carboxysulphate chemistry, actually, when you are using sulfide to be your source of electrons, in the same vein, you're also producing the corresponding radical, which in this case plays a very important intermediary step in bringing the synthesis to glycolic acid. And so in some cases, these radicals are very useful and very helpful. The hydroxyl radical in large quantities is what will happen if you allow UV light below UVC, at higher energy than UVC, to leak through into the water, is the part which is really destructive to anything. Now, if you go to 300 nanometers and still use ferrocyanide, you will stop producing large quantities of electrons. You'll start photoequating the ferrocyanide. And that's an interesting balance between producing electrons or photooxidizing and photoequating, which is also not very well understood. In fact, Zoe taught my student, who actually was working in Jack's lab, the famous one I mentioned in the beginning. She is working now on this in University of Washington. So in other words, the wavelength dependence really matters. If you use sulfide, for example, and you don't have UVC light below 250 nanometers, no electrons are produced. So 280 is no good. So you need the ferrocyanide if, you know. So all of them play a role, but the part which we know is destructive if you have UV light more energetic than 6 electron volts, because then nothing works, it seems. I hope I answered your question.
Dimitar, so firstly, an announcement for those of you who are watching on Zoom. If you'd like to ask a question, please type it in the chat. I'm happy to pass it along. But for that, I have my own question. So in terms of the UV and all the different roles that it plays, you know, thinking about how this could have played out on the Earth in the scenario that you had outlined, what do we know about the UV flux from the sun at, you know, when it was a few 100 million years old? How did it compare to today? And could you have too much, like, I mean, do you want to use the, you know, regular UV flux from the sun, or are you interested in it being a very active star of flares, providing like very, you know, intense energy at over small intervals?
Fred, that's a very important question. Actually, it's interesting. The answer is it's asymmetric. What is really difficult to repair or do anything about if you don't have enough flux. If you don't have enough flux, the dark chemistry takes over and you don't get anywhere. If you have too much flux, you get into trouble. But under these conditions, there are multiple ways in which this is alleviated. The first one is simply you go a little bit deeper. Most of this chemistry with the current fluxes, which are based on the sun as a star project that Ed Guinan and others did many years ago, and people are still doing. So we use, you know, that for the UV fluxes in the UVC for the early sun. At the current situation, because some of these products, including the ferrocyanide, which is not a product but is the started reagent, actually sunscreens, which means they absorb UVC light. They actually shield a lot of the UVC flux across the whole UVC range, deeper than about a meter or even centimeters in some cases. So I don't worry about having too much flux, because then the chemistry, instead of happening at, you know, 30 centimeters, will happen at 80 centimeters. Yeah, you pick your depth. All of that will work. These are all mixing. In any lake, that is a mixing layer, so you don't worry about the diffusion or whatever, layering and stuff like that. So my concern is about the M dwarfs. And even in their most active stages, they may not always have enough UVC flux at the same distances which the infrared flux is enough to keep the surface warm with the atmosphere and everything. So it will be different in different, but never worry about too much flux. That's my answer to this.
Can I just follow up on something you
Sure.
ferrocyanide as a sunscreen that will actually shield.
Right.
And so if there's too much, maybe, you know, and there are things that absorb a lot more strongly than ferrocyanide, like adenine.
Yeah.
So I know you've been looking at increasingly complex mixtures, so maybe you want to comment on, you know, what allows this prebiotic chemistry to happen or get cut off? Is there too many absorbing species?
Well, yes, I removed this from my talk because it would take more than an hour. But yes, again, Zoe Todd is implicated in some of that work, and we are now continuing what she started. What you cannot see there, but believe me, it's in those two diagrams, is a comparison of starting reagent, ferrocyanide, which both provides CN and the electrons, intermediate molecule, which in this case is 2-amino-oxazole, and final product, which is adenine or adenine nucleotide. I forgot the right word for it. So see, I'm still learning my biochemistry. So both the ferrocyanide, the initial, and the final product are very good sunscreens. They absorb UVC light. Slightly different wavelengths, but ferrocyanide is very broad, not much wavelength dependence. Adenine is more concentrated around 250 to 40. And then in the meantime, the intermediate molecule is not very photostable. It absorbs and gets destroyed, but you need it in order to get through the whole sequence. And so there is a balance there, which unfortunately you cannot see because it's very small here, under a given flux of what are the concentrations under which this will work. And the beauty in this is that it's a feedback which works. That is, if you have too much of the product, you block its production, but that means that's fine. You have too much adenine. Let's wait a little bit, take a breather. And you remember, there is always the night coming, sunset. So on a planet like the Earth, there was day and night. Then if you have too much of the initial reagent, ferrocyanide, okay, just wait a little bit and you'll get where you have to really worry about is in between. And in all of this network, the in-between works. So far, no showstopper. Is that what you were looking for? Or?
Yeah, I think it's going to be, obviously, it's going to take a lot of work to figure out. And, we start taking into account more and more products that are being produced, being degraded, and trying to figure out.
I think, my 5 cents on that is we're safe because if we have good sunscreens at the very beginning, and that's ferrocyanide or something similar, I mean, you cannot have cyanide salts without ferrocyanide. Iron is the main component, so you have to get to a Star Trek planet to get rid of iron. So that's not normal. And then we know already that most of our products, the monomers, are photostable. I mean, I kept saying that. So this is the perfect situation. You will always manage to get through as long as you meet the arithmetic minimum. So that's where I'm concerned. And the 2-amino-oxazole is just right to beat the arithmetic minimum, but it's hairy in some of the cases. So just to answer, between you and me, some of the amino acids that John is producing may be on parts of the network where this is not going to work. We just haven't had time to get into them. But at least that part, it works. So that's a good thing about it. Okay, yes.
Probably just continue with Jack's question. I just thought, I just quickly ask, instead of ferrocyanide, which can be the beginning of this photolysis, why can't you just do chemistry directly on ferrocyanide and you build a prebiotic, precursor of porphyrin? Something you have an ion there, you have an aromatic system, which is much more efficient.
Yeah, so in other words, use a different electron.
Right. The chemistry can directly down on the ferrocyanide. Then you build a ring system, and that system can provide free electron when there's a sunlight, right? Because free electron is really key for life. And once it's oxidized, it can go out and get reduced by whatever out there, comes back through some sort of trafficking. And that seems to me a much more efficient photosynthesis system.
Okay, so I agree with you that it will be a more efficient system. And the second thing I want to say, is that since I'm not a chemist and don't have the intuition, I cannot go through your argument in my head. So we need to talk afterwards if you could. So I do want to talk. But from an astronomy or geochemistry point of view, I want to say that we know we should have a lot of ferrocyanide. And so my practical approach to it is, if I can do it robustly with ferrocyanide, I just move on to the next problem that needs to be solved. Maybe once we have a working network, we will go back into it and start tinkering with it, just like a good car mechanic would, to improve it. And maybe we'll find something really dramatic, which will not just improve it, but make the whole thing so much better that will kind of get rid of the old. From a practical point of view, I'm trying now to solve the bigger problems. On the other hand, it is important to also make sure that anything that will, play a better role is also a natural product under the same conditions. And that part, again, because I don't have the chemistry intuition, I cannot tell you off the top of my head. But let's talk tomorrow and see if there is something we should look into. Yes, but porphyrin is of course great for you. Most of the control people just do that, as you know, they don't muck around with ferrocyanide, which destroys your cuvettes. You have to throw them out afterwards.
I think we have to get Toronto to involved in doing some prebiotic chemistry.
And
So this question comes from Steve Seidner. Going back to the scenario that you outlined earlier, the question is, are there issues pertaining to periods of drought versus good aqueous environments over time, such as the puddles form, concentrate reagents, they evaporate? How does this play into long-term modeling?
okay, so the dry-wet cycles have long been talked about in origins of life scenarios as very useful for a number of steps and some of the chemistry. David Dimmer is a big proponent of dry-wet cycles. I think John and Jack and I also like dry-wet cycles, mostly, however, for purposes of over time concentrating the reagents so that they can be used once the monsoon seasons come back and the lake is full. I think it will be difficult to think of the survival of a population of protocells under constant dry-wet cycles. If they're short-lived, probably that's no problem. But this is a problem that Jack deals with, and he feels, I think, that some dry-wet cycles are not going to destroy the population of protocells. But I think if at that point we don't have them, my personal feeling is better. And frankly, if you look at some of the geological record for old similar lakes, like in the Tumbiana Formation, or even on Mars, the Gale Crater Lake, you don't see episodicities of wet-dry cycles unless you look at near the beach. There are always parts of the lakes that are more or less continuous, and in the case of Gale Crater, the estimate is anywhere between 10,000 years and 1 million years. And if this prebiotic chemistry doesn't work in that kind of interval, of an order of 1 million year, then none of this will work. And that's my personal opinion. It's a fast process. There is accelerated evolution of the protocells, and they come to the point where no longer depend on eating off the land. And as a result of that, they can survive environmental changes like this. But in the very beginning, that will be difficult. Stockpiling, absolutely. That's how stockpiling happens, but that's before the prebiotic chemistry.
So I'm asking this question from way outside, and I'm just trying to see what. No problem, but I heard Jack's talk, and I've heard your talk, and one thing that I see common about this is the need for concentration. This seems to be the thing that is this a common theme? First of all, for the origin of life, to use as a whole. One question. Then second part of that would be, when you talk about the concentration of ferrocyanide, and you talk about concentration needing these photocells, are the conditions for both the same? Are you going to be looking for different places for these things, or do they have to be in the same place, and we have the same environment necessary for both?
Okay, I'll start, and then we'll see what Jack says. But you described two different steps or two different stages. So the generic answer to your question, it's a great question. The answer is yes. And the reason I'm saying it's a great question is because I myself didn't understand that for a long time. Jack and John will say, oh, you need high concentrations, but I didn't understand what and how long and how it works. Now I do, I think. Now, when it comes to ferrocyanide and some of the feedstocks, high concentrations simply exist necessary in order to accumulate enough of them. So in those brines, and then over a period of time, and then you can reuse them later on. When it comes to the protocells and actually using all of this, it's a slightly different issue, but again, all of this happens in relatively high concentrations. Although I've learned that when a chemist says high concentration, they mean a lot more. So basically, some of these concentrations are not considered high, but if you try to do this in an ocean on a very big deep lake, then the dilution factor is order of magnitude higher, including for things like the sulfide and the nitrogen species and anything like ferrocyanide and so on. So this is not going to work in an open basin, large lake, or a sea or an ocean from the part that I described. Now, the part that Jack is doing has slightly different requirements, but it can start and coexist with these environmental conditions for a long time. And that's a necessary thing, because otherwise the whole thing is not going to work. Off to Jack now.
Yeah, so at our stage of the process, a little later on, we're trying to have like replicating systems. Again, we need relatively high concentrations of sort of advanced chemical products. And so we're looking at different ways. Wet dry cycle is just one way of concentrating things. It tends to be a little bit destructive if you get too dry. Freeze thaw is another great way of concentrating solutions in between ice crystals. Temperature gradients, if they're strong enough by thermophoresis, can also lead to concentration effects that might be very useful. So there's really a lot to do. We have to find the right way of concentrating things that isn't also too destructive to this larger, more delicate systems. So it's just an ongoing project to try to work this out.
Do you know what impact the length of the day has on the ability of these protocells to evolve?
Yes, it does. That's a fun question and appropriate for the astronomer. Paul Rimmer in Cambridge actually is playing with this. They put together a small contraption for this kind of experiment. They call it the Star Lab, which can simulate, the overall light from the UV part of the spectrum, and they do the experiments in that environment. And you can also do the day-night. He has a nice paper from 3 years ago where he looked into fluxes, flares, as well as the day-night cycle. And we found it also useful with Zoe to use in some cases when we actually want to give the system a rest for a little bit, or we are afraid that we are not really robust and high yield enough, and that will erode the final product. So the generic answer is that you have to account for this. However, I don't know of a single part in the network where this is a showstopper or a serious problem. No matter how long the night is or how short the night is. Obviously, you have to have a daylight. And generally speaking, my sense of this, now having played with it in the lab at the right concentrations and the right fluxes, is the day and the UV exposure has to last more than a couple of hours per day. You will not get away with UV exposure, which is 1 hour a day, and then you have, many hours of night and then another hour. My gut feeling about what I know about the network is that this will start, the network will deteriorate and not produce enough monomers. That is something which needs to be done eventually. Actually, it's a worthwhile project to do. From a practical point of view, it's a little bit premature to do it now because we all don't yet have the full network working. We're pretty close, but not. And so starting to play with all these major environmental conditions is kind of premature, but we'll do it eventually.
So I have a question about the carbon source for these molecules, and you've shown cyanide as a carbon source. Is there any way, or is it not possible for CO2 or even better CO to be the carbon source? Because CO certainly can be incorporated in reactions with various metals, transition metals, and whatnot.
So the answer is absolutely. CO is incorporated somewhat in the cyanosulfidic chemistry, and that's why I like putting it in those diagrams as a minor species in the atmosphere, because we do think that in the early Earth there was a small amount of CO. The majority of the carbon in the cyanosulfidic chemistry, however, comes from the CN, from the cyanide. It's just the way, if you follow the way it's done now, that's what happens. However, with carbon dioxide, it's a very interesting thing. And thank you for asking the question. I have an additional slide on that. So basically, let's go there. So this is the cyanosulfidic chemistry as of 6 years ago. It's, the date is 3 years ago, but it's a little bit outdated now. Doesn't have a lot of the sulfur species. So you see here, essentially everything starts with the homologation of hydrogen cyanide. But if this happens between 6.5 to 7.5 pH, around neutral. If evaporation or some other processes, and especially if you're in a hydrothermal field and your closed basin lake has a more alkaline part to it, as the pH grows to 8 and beyond 8 and around 9, you transition to a network that looks like this. Now, carbon dioxide can simultaneously dissolve as bicarbonate in your alkaline lake together with the sulfur dioxide as sulfide. And now the UV light is really producing most of the electrons from your sulfide, producing that radical that I was talking about, and quickly going to produce oxalate, and then on to eventually glycolic acid, and some very interesting tartrates and interesting products, which eventually from the glycolate, you end up with things like malate and succinate, and the things which we know and love about the core metabolism. So that happens at 9. And that here, all the carbons come from the carbon dioxide from the atmosphere, dissolved in the water. So that's the carboxysulphatic chemistry I mentioned when I was telling the story about Sucrit giving the talk in Cambridge. And so the way John thinks about it is as a progression from heterotrophy, which is the cyanosulfidic chemistry, which is around neutral waters, to the more alkaline carboxysulfidic, which produces very useful molecules for those protocells, which eventually can just rely on carbon dioxide from the atmosphere, which is the major source after all. So you're no longer limited to the carbon that comes from the cyanide. This is a good thing because eventually that's going to run out. And if you haven't learned how to do your own, manufacturing inside the cell, you're dead because you can no longer get the monomers for your survival from the outside environment. So that progression is necessary, and maybe that's how it happens, with the pH shifting towards alkaline and carbon dioxide getting involved in a very similar way with the help of sulfated electrons produced by the UV, but this time using sulfide. But this is answering your question, kind of?
Okay, one last question.
Hi, I'm just an undergraduate physics major, so I hope this isn't too basic. Could you contextualize for me a little bit the link between having these concentrations of change of nucleotides of amino acids and then arriving at that first replicator or protocell? What kind of things need to happen, and how long are you expecting to sit there with these concentrations until they do?
Well, the way I imagine it is better shown as a set of cartoonish block diagrams, if I may show you. And I think this is what you're asking, the phases and connections between those phases, the way I see them. So you start with the planetary feedstocks molecules and stuff. Water is stuff. You have to be in liquid water. The astronomical environments I talked about, UV particular. And then you go through phase one. Phase one is the jump starting, the spark and the fire, and but then you have to kind of provide firewood, Eventually, very quickly, tau 1 is a very short time scale. As I said, happens during the day, hours to days. You make the monomers and the precursors, and we are waiting on Jack to do phase two. But when phase two happens, those protocells look and behave like real cells, with one very big exception. They do not make their building blocks. The building blocks come from phase one. The time scale tau 2 is relatively short, but this whole part, let's call it the RNA world, although it's not necessarily, that's a misnomer here, but that whole part has to last long, because this is the time when RNAs or whatever genetic molecule you have explore gene space. They have to figure a way to both build a few enzymes and to know how to wean themselves off from the environment, meaning to make their own precursors and monomers like every cell does today. So that has to last long, because eventually you want to end up with what we have today, self-sufficient protocells. Some people would call it the last universal common ancestor, or whatever. So to me, that tau 3 is the long one. And so here you have what I would call a supply chain. This supply chain has to be robust. Tau 1 to tau 2, tau 1 to tau 2, to maintain this where RNA can explore gene space so we can get to this. I hope that one day very soon, maybe in a couple of years, Jack will have this, and then we'll use it as a tool, as a toy model in the lab, to actually find out how long tau 3 takes. Tau 3 is this exploration of gene space. Right now you can't do it because none of the even simplest living things on this planet are simple enough that we can do this. There is no model or tool with which you can do this. You'll have to make it yourself. Jack will have to make it. And then one day you'll cut off the supply chain, and you will be directly using the planetary feedstock, as we were talking about carbon dioxide and all the other stuff. But you will not need this. So this is the precarious part of this whole thing. This has to last long enough and be there for you to get to that, because that gene space is large. We don't know how long it takes. We will find out experimentally. I don't think theoretically you can actually say.
Maybe hard enough experimentally.
Hard enough experimentally, yes. Did this answer your question? Yeah.
Okay, great. Thank you very much.
Thank you. And Fred, so we have a meeting right now. I'm looking forward to see you.
Yeah, no, I've been looking forward to your visit. I'm sorry I missed your talk yesterday. I had an appointment, but I know Astro recorded it, so I'll take a look at it.
Excellent.
When I'm able to.
Oh, see. Yeah, let me just.
Let me get out of this.
For the